My name is Yuji Yamamura. I am a graduate student of Osaka State University, Japan. I would like to talk about a part of my research, velocity characteristics in wake of a non-sphere body and in pore of porous media composed of non-spheres. In particular, I would like to focus on the velocity characteristics in the wake of a single prolate spheroid in my talk. Nature is full of porous materials. The sandy beach is a typical example. Such porous structures have been frequently created artificially and used for these purposes, such as wave energy attenuation, adsorption of suspended substance, promotion of diffusion of dissolved matter, and so on. It is easy to imagine that fluid motion in the pores and around the porous body would affect these functions. However, the fluid motion in the pore of porous media has been still unclear. Therefore, it is essential to get knowledge of fluid motion in the pore. Previous studies on porous body have been done experimentally using porous media model composed of spheres and real pebbles. In pores, it can be imagined that the shape and orientation of solid composed porous body affect fluid motion. Studies on fluid motion around a single object have been carried out. For example, the flow motions around a sphere in uniform flow and a 6x1 prolate spheroid in cross flow have been investigated. As for the study on a sphere, it is reported that the characteristics of the hairpin-shaped vortices change with the Reynolds number. As for the study on a prolate spheroid, the wake of this spheroid becomes unsteady beyond the Reynolds number is larger than 100, whereas the wake of the sphere becomes unsteady beyond the Reynolds number exceeded 250. This means that characteristics of fluid flow transitions vary with the shape of the solid. Kadoya studied the aspect ratios of more than 1,000 crushed stones and found that most of them had aspect ratio in the range of 2:1 to 2:3. Therefore, with the ultimate goal of characterizing the pore flow characteristics of porous bodies composed of solid with low aspect ratios, the present study aims to elucidate the detail of the flow around a single prolate spheroid. I would like to explain the experiment apparatus. I used a U-shaped pipe room with rectangular across with 0.2 meters height and 0.1 meters wide. Uniform flow was generated by a pump. A sphere and spheroid were made of polycarbonate by 3D printer. The diameter of the sphere was 2 cm. The major axis and the minor axis of spheroid is respectively 3 cm and 2 cm. The model was fixed at the center of pipe room by polyethylene strings. The flow was visualized using the laser light sheet. The captured image size was 1920 pixel times 1200 pixel. The spatial resolution of the image was almost 0.01 cm per pixel. Frame rate was 150 seconds and exposure time was 1000 seconds. Acquisition duration was 50 seconds and the number of images was 750. The coordinate system was set up as shown in the left figure, with the center of the model as the origin. The x-axis was set in the flow direction, and z-axis was set vertically downward. The right figure shows how to fix the model. The experimental conditions are shown in this table. The approaching velocity to the model was about 4 cm per sec, and the attack angle of a spheroid was -3, 12, 30, 49, 58, 88 degrees. The Reynolds number of a sphere and a spheroid were calculated respectively by the equations as below. The velocities around the sphere and the spheroid were measured using the PTV technique. The super-resolution casing method, developed by Dr. Takehara, was used as the algorithm for PTV, since the velocities were measured at the point where the tracer particles are detected. Velocities at a given grid point are obtained by spatial averaging measured velocities in a certain region. The velocities at a given grid point were obtained as the average value of the velocity vectors in the circle with the radius 0.25 cm was defined. After removing the outlier measurement by detection using an index of 3 times of the standard deviation, the velocities at the grid point were determined. The turbulent velocity is calculated by subtracting the spatial average velocity from the measured velocity. Then, I'd like to show the experimental results. This animation shows the spatial average velocity distribution in the central cross-section of a spheroid with attack angle of 30 degrees. In upper region of the wake, a clockwise vortex was varying size flows downstream, while in the lower region, a counterclockwise vortex is stationary. This animation shows the result in the central cross-section of a spheroid with attack angle of 58 degrees. In an upper region of wake, a clockwise vortex are stationary, while a counterclockwise vortex shows downstream in the lower region. These figures show the snapshot of the spatial average velocity vector at certain time with attack angle of 30 degrees and 58 degrees. It is found from these figures that the size of the vortex in the wake seems to depend on the attack angle, and that the vertical head of wake depends on the vertical head of spheroid. These figures show the measured velocities at x equals 2 cm in the central cross-section of a spheroid with attack angle of 30 degrees. For the horizontal component, the velocities at z equals -1, 0, and 1 cm in the wake slower than those at z equals -2 and 2 cm out of the wake. The velocities in the wake seem to have high frequent fluctuation but no periodic variation. For the vertical component, velocities in the wake seem to include some periodic velocity variation with small amplitude. These figures show the measured velocities at x equals 4 cm. For the horizontal component, the velocities in the wake contain the periodic velocity variation with 0.85 cm per sec maximum velocity amplitude, and the velocities out of the wake also seem to contain the periodic velocity variation. Further, the obvious phase shifts are observed between different measurement points. For the vertical component, a periodic velocity variations are observed as the same as the horizontal components. But the velocity amplitudes seem to tend to be smaller at the lower measurement point. In addition, obvious phase shifts are not observed. These figures show the measured velocities at x equals 2 cm in the central cross-section of a spheroid with attack angle of 58 degrees. For the horizontal component, the velocities are almost constant at any measurement point even in the wake. For the vertical components, there might be some periodic velocity changes at any point. These figures show the measured velocities at x equals 4 cm. Both velocity components, especially measured in the wake, present complex time histories and seem to contain several periodic components. Next, I'll show you the result of distribution of turbulence intensity. The measured turbulence intensity includes information of turbulence as a background of flow in pipe flume and of turbulence induced by the presence of spheroid. Therefore, the turbulence intensity due to the presence of spheroid was obtained by subtracting the average of turbulence intensity in the upstream region which was not affected by the spheroid, from the measured turbulence intensity. These figures show the distribution of turbulence intensity of a horizontal velocity component in the central cross-section of a spheroid at each attack angle. The turbulence intensity is normalized by approach velocity. The distribution of horizontal turbulence intensity for a sphere and a spheroid with -3 degrees and 88 degrees attack angle are vertically symmetry. The others are asymmetry. Regions of large turbulent intensity emerge from the top and bottom of the spheroid and extend downstream. On the other hand, there is a region without the significant turbulence intensity behind the spheroid. These figures show the distribution of the vertical turbulence intensity. It is found that the maximum intensity appears around x equals 4 cm. The height of the region with the significant intensity seems to be dependent on the projected height of the spheroid in the flow direction, and the area with the significant intensity spread downstream wider than the horizontal component. These figures show the distribution of non-dimensional shear velocity. From these figures, it is found that negative shear velocity regions appear from the top of the spheroid, and the positive one appears from the bottom of the spheroid, and the distribution of them resembles one of the horizontal turbulence intensity. The main conclusions of my study are summarized here. The velocity field around the sphere and the prolate spheroid was measured in detail. Horizontal and vertical velocities in the wake change with complexity. The properties of the velocity change depend on the attack angle. Turbulence is generated from the top and the bottom of the spheroid, but there is the area without the significant turbulence intensity behind the spheroid, and the size depends on the attack angle. The distribution area of the shear velocity is almost consistent with that of the horizontal turbulence intensity. I would like to finish my presentation. Thank you very much for your kind attention.